Welcome to our first afternoon session with the Stout Student Award winners. There's a whole slew of them on the calendar. I don't know if you saw through the online browser, the schedule, that you can tell which ones are Student Award winners, and that's one of these sessions today. We have 3 speakers. The first is Katie from NC Central. The second is Jackson from Elon, and the third is Sarah from UNCW. So each speaker is going to give a brief intro on who they are, and then jump right into their presentations. I will keep time on here because I don't see the handy dandy slide paper to tell you when it's 5 minutes. Mm-hmm. But as soon as the talk is over, we'll have about 5 minutes for questions, and then the next speaker will start right on the times on the schedule, so that if you need to move rooms, everybody's staying on schedule. Does that sound good? Okay, welcome. Caitlin, it's all yours.
Perfect. Hi, everyone. My name is Caitlin. I am in my last semester of my master's degree at North Carolina Central. My research has been focused on testing different spatial interpolation methods to best measure air quality in North Carolina. So, in 1970, the Clean Air Act was enacted. The United States Environmental Protection Agency named 6 air pollutants to be monitored. These were carbon monoxide, lead, nitrogen dioxide, particulate matter, and ozone, which is what my specific research is based off of. Those are the figures that I use. The air quality data is downloaded from the EPA's Air Now and Air Quality System and can be placed into GIS. Because station data is monitored through monitoring sites that are sparsely located throughout the state, you need to apply interpolation techniques to be able to show those predicted surfaces across the state for better environmental policy enactment. So my research question was, which interpolation method is best used to represent ozone in North Carolina? High air pollution levels can be considered an urban phenomenon by a lot of researchers, but ground level ozone can be transported long distances by wind. This is another reason that interpolation methods are really important, as they will account for that ground level ozone as it transports. So accurate mapping is essential in identifying high exposure areas. I used kriging, which accounts for spatial autocorrelation and will provide uncertainty estimates. Inverse distance weighting, which is a deterministic approach that assumes the closer points will have more influence on the estimation, but could struggle with capturing spatial variability. And then spline, which does create that smooth surface by minimizing curvature throughout the data, but it could oversimplify the data. Some prior research that I found in this specifically was some spatial modeling of particulate matter 2.5 concentrations in Tehran, Iran. They compared kriging and inverse distance weighting. They have a population of about 10 million. It's the highest populated city in Iran. This study specifically focused on particulate matter 2.5 because of its environmental health hazards and public safety hazards. So across the city, they have approximately 25 monitoring stations. You'll see that in the top right. To compare each model, they ran root mean square error and mean error to test the accuracy of the predicted values for each monitoring site. So they compared, you'll see sorry, I thought that I had this. I thought that I could see this. So this shows each map, and they use ordinary kriging and universal kriging. So this is a comparison of those 3 maps. The hotspots change throughout the city That's what they were really looking for, kind of see which model would best represent hotspots for this area. It does show hotspots in the south of using each interpolation method, but they wanted to find where those minimal hotspots could be as well. Overall, they did find that using Kriging specifically helps represent areas that are more vulnerable to the high ozone values. So you'll find that using that model helped them represent areas that are affected by that urban phenomenon of ground level ozone. So another prior research was using spatial modeling for mapping tropospheric ozone in eastern Texas. So there are approximately 100 monitoring sites in Texas, and they are sparsely located across the state. But this study specifically focused on eastern Texas, as eastern Texas houses majority of those urban populations. They used Kriging interpolation because they think the main advantage of using it was the ability to calculate those uncertainty of prediction, which is useful for decision making. When viewing the interpolated maps, which is down on the right-hand side right here, you will see that the highest values are found in similar areas for each monthly data that is represented. They found that using Kriging interpolation helps represent the areas that are vulnerable to high ozone values. You'll notice this because of the high concentrations that are found around these urban populations. So my data specifically was downloaded from EPA's Air Now and the air quality system that the EPA uses. Ground level ozone specifically is measured in parts per million, and the 8-hour maximum concentration is reported. My years that I used was everything that was available, which was from 1980 to 2024. And this specific set of data also includes the air quality index for the day that concentration was recorded for each monitoring site. So this is what it looks like on that EPA Air Now. You can choose any of the pollutants that you'd like to look at. You can choose the state, the monitoring site. You can break it down pretty specifically for which pollutant you would like to use and which pollutant you would like data for. And then, so across all of the data, this map represents all of the monitoring sites in North Carolina for the last 40 years. This does represent the monitoring sites that are not in use and that are currently in use. And this is the monitoring site ID, the amount of levels that they recorded in the last 40 years, and their corresponding county. So my methods, the first thing I did was merge 5-year data increments. So I took all of the data and merged them into 5 years. These were the total measurements for each year. The next thing I did was build a geoprocessing model. So I wanted to take my standalone tables and export them into spatial data. Then I ran a summary statistics. I wanted my site ID first, and then I just did the mean of the site lat and the site long so I wouldn't lose those values. I did the mean and the standard deviation for the maximum 8-hour concentration, and I went ahead and did the mean for the daily AQI, just so that in further research I could use this same data set to further my knowledge on the corresponding values and what they could mean. So for Kriging, I did the ordinary Kriging model, and the semi-variogram model that I used was spherical. This is important so the spherical model it will show a progressive decrease. Sorry, I want to make sure I get this right. Show a progressive decrease of spatial autocorrelation, which will be an increase in the semivariance until some distance beyond which that autocorrelation is 0. This became significant once the maps were made and my predicted values were extracted, as the predicted values for my specific data were showing that they were underestimating a little bit. So I think changing this in the future could help with that. It could mean that this specific method could be better for certain data sets. And then for IDW, I just did my standard search neighborhood. I used a 2-power. All of this is the settings that ArcGIS Pro will give you when you use IDW. And then for spline, same thing. I used the exact parameters and environments that ArcGIS Pro will give you when you run this interpolation method. And then for each of these, I used my county map, my county feature layer as my mask, so that I could make sure that the output predicted surface had the best fit and showed the best set of data visually. So for spline, this data runs from 1980 at the top left to 1999. These are some of the first maps I did, and I was kind of taken back, mainly because you see higher values, like right here, you see the highest values in this specific data set in areas that don't have the monitoring sites. So I was trying to figure out why that would be happening. That's why I used statistical evaluations after making the maps to kind of see what that meant, what it meant for me and my specific data. And then this is for the years 2000 to 2019. You do start to see the overall ozone range start to go down as you move further into the data. So for 1980 to 1999, for spline, Kriging, and IDW, I did see a higher range. You'll have, this is for 2020, I know that I have values, that's what I was looking for. So you see those high ranges in the 0.06s, and that the EPA's standard for ozone is a 0.07. So once you move to these newer maps, you do see that climate change policy has began to work. So some major takeaways for spline. The big thing with spline 2 was there were negative predicted values for all of the years except for 2005 to 2009, 2010 to 2014, and then 2015 to 2019. So my highest values were found in the southwestern mountains, and then highest values. And then once you got to 2005 to current, you're getting mid-range values across the entire state. Same thing with IDW. Very odd spatially until you get to post-2000. That is also when you start to get more monitoring sites across the state as well. And then you also see these ranges start to decrease. For 2020 to 2024, kind of odd, you see a really high ozone concentration around that monitoring site in South Yancey County, which is kind of an anomaly as normally in the mountains you would think really clean air. So further exploration might show why is that so high? What happened during these 5 years that would make the ground level ozone that high, which is something that I hope to do in the future. So your major takeaways for IDW, it's going to be your highest values for 80 to 84 are in the Piedmont region and the northern coastal region. And then 85 to 89, you see lower values statewide with higher values found in Granville, Durham, and Lincoln counties. And then for 90 to 99, those 2 5-year data sets, you see very spatially similar predictive values with lower values in the southwestern counties and the coastal plains. And then after 2000, you see low predictive values in the southwestern counties, Cherokee, Clay, Graham County, and then high predictive values in the eastern Piedmont from Mecklenburg County north to the Rockingham, Guilford, and Forsyth County area. And then for Kriging, Same thing. You see that very odd visually and spatially odd spread of ozone concentrations from 80 to 84. And with a high range value at the monitoring site in Edgecombe County, which is eye-catching if that's the only spot in the state during this 5-year data period that has a high value. Then they become more visually and spatially. You see the spread, and that makes a little more sense. Same thing with 2000 to 2004. Initially, the odd spatial spread from 80 to 84, I came to the conclusion that it might be because there was only 25 monitoring sites in that data set. Then we have a visually odd 2000 to 2004 with 52 monitoring sites. So that's one of those things. Further exploration might help. Was the AQI high? Was the AQI low? What was causing the ozone to act the way that it was acting? And then this is for 2020 to 2024. Your highest value, ranged predicted value, on 20 to 24 for this one is a 0.0429 to 0.043. So overall, that's 0.03 parts per million less than the standard set forth by the EPA. So if we're going to go back, we're going to base it on the value from 1980 to 84. That value is a 0.559. So over the years, North Carolina has combated the air pollutant problem that we've had in the state, and that's even with predictive values, we could make that assumption. So your major takeaways for this would be from 80 to 84, again, you have that unusual spatial spread with a small area of high concentrations around the monitoring site in Edgecombe County. And then your lowest predicted values for 85 to 89 and then 90 to 94 are the coastal counties and southeastern counties. With this is one of the ones where it was like the predicted values are the highest in areas with a high urban population, like Mecklenburg County, the Raleigh-Durham area. And then much like IDW, the higher ozone concentration areas move a little farther west to extend from south to north in the eastern Piedmont with lower values along the coastal areas. So my conclusions, I went through and extracted all of the predicted values for those monitoring sites for each 5-year data set, and I ran the root mean square error on them. So everything that's highlighted in a dark pink is the minimum root mean square error for those predicted values when compared to the observed values. Statistically, IDW is the most significant for all of the states except for, or for all of the data sets except for 95 to 99. But spline being the minimum in that, the problem comes from, we know that in 95 to 99, I had low predictive negative values for spline. So this almost discounts spline because we are getting the negative low end values for majority of the data sets. And then for kriging, you have the highest root mean square error for each data set, but you tend to underestimate variability. Where I came to this conclusion was comparing the observed mean of the entire data set and the observed standard deviation of the entire data set, and compared that to the predicted mean and the predicted standard deviation. The standard deviation for the predicted values is lower than the standard deviation for the observed values. So you could conclude that this means that the kriging is underestimating and in its variability. And then, so overall, IDW would be the most statistically significant for displaying air pollution data in North Carolina. Some of the future work that I really want to do, so I want to add to my geoprocessing model. I really like doing that. I like that side of it and being able to run more things at once. So I want to add the extract values to each interpolation method. I would also really like to try using different kriging methods. So because I'm using the semi-variable or the semi-variogram method, a spherical, it could be underestimating those values. I could fix the underestimation by trying different methods. So I really hope to try that as well. That's kind of where trying different parameters, maybe changing my powers, seeing if that changes, trying different spatial scales. So when we were looking at the prior research in Texas, they were only using an eastern portion of the state, where a majority of their monitoring sites were. That's why kriging works so well for them. They were using a smaller portion where a majority of the monitoring sites are. So maybe if I took just the Raleigh-Durham area, where there's a lot of monitoring sites, or just the Mecklenburg area, would that mean that that would be the best interpolation method for me and to display this? I would also love to do that on the other side and add more. Add Eastern Tennessee values, like Southern Virginia values, Northern South Carolina values, adding those values in and seeing if that would change, because maybe the problem is I just don't have enough monitoring sites, because that could be why my spatial spread is odd visually. I'm getting negative values in spline. That could be why. So maybe there just aren't enough sets of data. And I would love to try other air pollutants. So PM 2.5 and PM 10, nitrogen dioxide, seeing if that would also change, if I'm going to see the same thing across the board for every air pollutant. And then I would love to look at highly urban areas compared to rural areas. In North Carolina, it's a little odd. We have high urban areas, but in our small rural areas, we have Lake Smithfield. Smithfield's not that big of a city, but we have the Smithfield plant there. Would that change? So I'd love to explore that as well. That's it. Is there any questions?
We have about 7 minutes or 5 minutes for questions. Yes.
Yeah, I was just curious if you thought about incorporating any independent variables, effects and mobility of particulate matter, like tree canopy, in the water, or planning safety with that.
No, but that's interesting that you say that. So particulate matter is a little more variable than ground level ozone, I want to say. From what I understand, I could be wrong. I want to say particulate matter moves a little differently. So ground level ozone can be transported, but its main characteristic is that it comes from car emissions. So when you look on the EPA and you read about ozone. So I haven't thought about adding that in. I would be interested to know if it would change though. The one thing that I did think about adding in was seeing if, like comparing those, like comparing Mecklenburg County to Durham County or Mecklenburg County to Forsyth County and seeing if that changed anything.
What about adding traffic data?
So I would also love to do that. I thought about that as well. I just don't know how I would do it. That's the thing. I can't I've done this for so long. So I'm wondering if I could add it into the geoprocessing model. Like, could I do a compare and contrast? And that might be something to explore as well.
One option is a regression. You have
Okay.
ozone as your one variable that you're testing, and all these other independent variables.
Okay.
Topography and then cover.
Okay. Interesting. Yeah, I'm gonna write that down in my notebook. But yeah.
Okay, we've got a few minutes for our next speaker to come on up. Thank you very much.
Thank you guys.